The battle for global telecoms dominance is moving from the Earth's surface to Earth's orbit. America and China are sprinting to lock down the sky in order to dominate the coming technologies like AI and 6G satellite mobile. SpaceX's Starlink and Amazon's Leo aren't just beaming down broadband, they are rolling out direct-to-cell service and plotting full-blown data centers suspended in space. Throw in autonomous cars, eVTOL air taxis, drone networks, and relentless rise of AI into that equation, and it becomes terrifyingly simple. The nation that owns low Earth orbit owns the planet's infrastructure. That's a reality Russia and other lesser powers refuse to accept. They see the trap, fall behind now, and you will be held hostage to a foreign power satellite for most of your critical networks. So these nations are scrambling, pouring everything into their own orbital competitors, because in this new era, dependence isn't just an inconvenience, it's a weakness that will be exploited. Russia's legacy as the pioneer of satellite technology is forever etched in history with the 1957 launch of the first satellite, Sputnik 1, an event that stunned the world and ignited the space age. For several years, the Soviet Union maintained a commanding lead, launching the first animal, first human, and first woman into space. However, this early supremacy proved unsustainable in the long term. The United States, after an initial period of catch-up, not only matched but surpassed Soviet capabilities through programs like Apollo, the Space Shuttle, and the development of a massive diversified satellite infrastructure. While Russia remains a significant spacefaring nation with a substantial portfolio of satellites and with its own global navigation system, it's now regarded as falling behind the new leading powers, the United States and China. Its satellite fleet, while robust in certain areas like military reconnaissance and secure communications, has struggled with modernization. It has a respectable amount of aging TV broadcast satellites, but it's very behind when it comes to broadband satellites. To address this satellite deficiency, Russia launched the Sphere constellation in 2018. Russia's Sphere satellite constellation is a state-backed initiative designed to comprehensively modernize the nation's space-based infrastructure and reverse its declining competitiveness in the face of systems like Starlink and OneWeb. Initially proposed as a constellation of 640 satellites by 2030, the project will later be scaled back to 162 satellites with a budget of approximately $2.5 billion. Its core purpose was to provide Russia with sovereign, all-encompassing space services from broadband and television broadcasting to Earth imaging and Internet of Things connectivity, while also supporting government services and Arctic communications. The constellation was structured into distinct satellite groups for telecommunications and Earth observation, each with a specialized function. The SCIF group of 12 satellites at about 8,070 kilometers in medium Earth orbit was to serve broadband internet access. The Marathon group of 271 satellites at about 750 kilometers in low Earth orbit was to serve Internet of Things. The Express RV group of 4 satellites in high elliptical orbit was for broadband internet coverage of the Arctic region and Northern Sea routes. The Yamal and Express groups were 8 large geostationary orbit satellites for communications and TV broadcasting. And lastly, the Berkut, 5 groups of 68 satellites for Earth observation in various spectrums, including satellites for high detail imaging and radar scanning. A SCIF prototype satellite was launched in late 2022 to test Ka-band communications and secure orbital frequency rights. 5 Marathon IoT prototype satellites were planned for 2023, with 44 production satellites slated for 2026. Roscosmos planned to start serial production of Marathon and Berkut satellites by 2027 as part of the federal project. State-owned satellite manufacturer Reshetnev was the lead developer for most of the satellites. This included the SCIF broadband satellites, the Marathon IoT constellation, and the Yamal and Express series for broadcasting. The other manufacturer was NPO Lovachkin, renowned for its expertise in interplanetary probes and complex scientific exploratory vehicles. They are responsible for the sophisticated Earth observation satellites of the Berkut series, which require advanced optical and radar imaging technology. But despite political backing from the Kremlin, the program has encountered substantial technical delays, budget cuts, and a struggle to commercialize its services. In 2022, Roscosmos under new head Dmitry Bakhanov abandoned the Marathon IoT satellite constellation and the Skiff Broadband Group, stating there wasn't a good enough business case for those services. The reported termination of the Marathon IoT constellation sparked debate among space experts in the country, highlighting a fundamental strategic divergence in the nation's approach to satellite communications. Proponents of the system defend it as a crucial sovereign asset. They argued that Marathon IoT was uniquely positioned to fulfill the military task of controlling unmanned systems like drones, citing its solved supply chain for both space and ground components and ready production capacity for user devices. They emphasized its export potential and warned that its cancellation will strike a blow to Russia's technological sovereignty and cooperation with allied nations. Technically, Marathon IoT was designed around the LoRaWAN protocol. It planned two payloads, one for standard IoT sensor data, with delays over 2 seconds, speeds of about 6 kilobits per second at 863 to 928 MHz for compatibility with terrestrial networks, and the modified version for unmanned aerial vehicles command and control. This second payload aimed for 250 milliseconds latency and speeds of up to 31 kilobits per second. Its developers claimed they were sufficient for transmitting imagery and meeting typical UAV control requirements. However, critics contend the project's closure was both expected and justified. They viewed Marathon as a technological dead end, describing it as an underdeveloped LoRaWAN in space that locked Russia into a protocol with inherent bandwidth and latency limitations. This, they argue, created a strategic impasse, especially for future military applications requiring high data rate links, and risk embedding outdated technology into critical drones and defense infrastructure. This criticism is bolstered by a visible shift in focus from state agencies like Roscosmos and FPI towards next-generation 5G-based direct-to-device D2D systems. A new competitive ecosystem of private companies is now advancing this vision. Private companies, Geoscan together with GoNet, are developing two satellite constellations, a low Earth orbit constellation for telecoms communication, data transmission, and IoT, as well as a communications constellation to compete directly with the Iridium system. Another private company, the Sputnik's company, a sister organization to the MTS mobile operator, plans to launch two 5G direct-to-device cellular communication satellites into orbit in the summer of 2026 for testing. A startup named the Telecom Project 5 on May 2025 tested its 5G direct-to-device satellite prototype by simultaneously controlling 5 drones from a TVS-2MS aircraft that carried their prototype satellite to atmospheric heights. Another startup, the Technovation concern, is developing a 192 satellite low Earth orbit constellation based on twin 6U CubeSats units for broadband, conducting research in agriculture and analyzing traffic. The pivot to 5G direct-to-device standards promises far greater data speed, lower latency, and seamless terrestrial network integration, which are deemed essential for future civilian and military needs. Consequently, with multiple entities pursuing more capable alternatives, the continued investment in the limited Marathon IoT system became difficult to justify from a long-term strategic perspective. Russia also didn't and couldn't realistically sustain multiple competing satellite broadband constellations, so the state-developed Skiff constellation was abandoned in favor of private constellations like the ones from Bureau 1440 and the Sputnik concern. But the High Elliptical Orbit Express RV constellation for broadband in the Arctic regions of Russia was funded because private companies were not interested in launching satellites into latitudes with very sparsely populated areas like the Arctic. The Roscosmos subsidiary Reshetnev plans to launch all 4 of them to orbit in 2026. The system is designed to provide broadband internet to the entire territory of Russia, including hard-to-reach regions and waters of the Arctic Ocean. It is planned to achieve coverage in high latitude by placing the satellites in 4 planes in a high elliptical orbit. Each of the 4 satellites will be equipped with equipment to operate in 3 frequency bands. including 12 Ku-band antennas as well as C and L-band antennas as part of the onboard relay complex. The first of them is planned for orbit at the end of 2026. Reshetnev and mobile operator Beeline have agreed on the development of a satellite communications system that will test the integration of the satellite technology with 4G and 5G terrestrial networks to provide 5G NTN mobile coverage in remote regions of the country. Instead of a few robust, well-funded competitors, Russia risked creating multiple partially deployed systems, none of which would achieve global competitiveness or full domestic coverage. Russia's satellite broadband ambitions would have remained fragmented, slow, and perpetually in development, squandering resources and strategic opportunity. With the appointment of the new head of Roscosmos, Dmitry Bakanov, in 2025, the closure of the Skiff and Marathon programs was a step in pruning the ecosystem and leaving the satellite constellation business to private companies. Roscosmos wants to focus on rocket-launched vehicles, whilst most of the satellite making is outsourced to private enterprise. This represents a fundamental cultural change for Russia's historically state-dominated space sector, aiming to inject agility, specialized expertise, and cost efficiency into its beleaguered space sector. Russia's main competition for Starlink is the Bureau 1440 constellation known as Rasvat or Dawn. Bureau 1440 is a private aerospace company developing this low Earth orbit satellite constellation for broadband internet. The company's name is a homage to the 1,440 orbits completed by the Soviet Union's pioneering Sputnik satellite in 1957. It is a subsidiary of the Russian conglomerate IKS Holding, which also owns Yadro, a company which manufactures computers, servers, switches, and telecoms base stations. IKS Holding also has a subsidiary called Centacor, Russia's number 2 RISC-V chip design company, behind the Cloud Bear company. Bureau 1440 plans to create a system with performance and scale closer to Amazon's Leo 3000 satellite than to Starlink's vast over 10,000 satellite network. According to documents filed at the International Telecoms Union, the Bureau 1440 project follows a single-shell strategy at 800-kilometer orbits with an inclination of 98 degrees, providing latencies of between 48 to 70 milliseconds, compared to Starlink's more responsive 550-kilometer orbit, providing latencies between 25 to 40 milliseconds. The first 3 test satellites were launched on June 2023 from the Vostochny Cosmodrome. A few days later, the engineers conducted the first communication session. The speed was 10 megabits per second and the delay was 41 milliseconds. In August 2023, the engineers of Bureau 1440 managed to conduct the first satellite video communication session in Russia, on Mount Fisht, in the Republic of Adygea, an area without cellular network coverage. The company's mission control center in Moscow established a stable connection with the team on the mountain. In 2 years, these prototype satellites made more than 11,000 orbits around the Earth, and the Mission Control Center conducted over 8,000 communication sessions, receiving and processing 2.9 terabits of telemetry and target data. 3 second-generation prototype satellites launched in May 2024 helped the company work out the antennas in the Ka-band with frequency radio waves between 26.5 to 40 GHz. The satellites became twice as large in size as they carried space-to-earth satellite communications equipment and intersatellite laser communication terminals on board. They introduced the intersatellite laser communication to ensure that the constellation allows data rates of up to 1 gigabit per second with a delay of less than 70 milliseconds across the globe. Laser communications in orbit solves several problems at once. First, it allows the transmission of huge amounts of data in a much shorter time than traditional radio channels. Secondly, optical transmission provides a high degree of information protection. But the main advantage is the reduction in the need for ground gateway stations, special communications facilities with large antennas that receive a signal from a satellite and connect it to the terrestrial internet backbone networks. Satellites connected by laser channels can transmit data directly to each other, forming a single network in orbit. At the same time, global coverage is provided without the need to have an extensive terrestrial infrastructure in every point of the planet. This is especially important for hard-to-reach regions where the construction of ground stations is economically inexpedient. In June 2024, as part of its second test mission, Bureau 1440 conducted a successful communication section using the 5G NTN protocol for the first time in the history of Russian cosmonautics. The 5G NTN standard provides seamless integration with mobile operators. A 5G NTN compliant satellite becomes just another cell in a mobile operator's network. Phones roam automatically between terrestrial 5G and 5G satellites. If a constellation follows 5G NTN, it instantly becomes compatible with other mobile operator systems and current devices. This will make it easier for them to upgrade their satellites to serve direct-to-device functionality. Regulators prefer standardized systems because they follow ITU-aligned power and interference rules. Thus, coexist better with terrestrial networks and support emergency services and lawful intercepts. A constellation aligned with the standard has future-proof evolution and automatically benefits from Ku-band NTN, multi-orbit mobility, regenerative payload support, and direct-to-device broadband. In a broadband 5G NTN system, the satellite functions as an extension of the 5G radio access network, transmitting 5G radio waveforms toward a fixed or mobile subscriber terminal on the ground. These terminals, often called CPEs, VSATs, or 5G NTN gateways, use a directional antenna such as a mechanically steered dish or flat panel phased array. Because broadband service requires high throughput, the satellite typically operates in Ku or Ka bands, where wide bandwidths are available. The terminal locks onto a satellite's spot beams, synchronizes using 5G NR procedures, and compensates for the long propagation delay inherent in satellite links. Once synchronized, the terminal completes the standard 5G attached process, authenticates the network, and establishes user-plane connectivity through 5G. 5G NTN uses specific satellite-friendly frequency bands defined by 3GPP, mainly in the L-band, S-band, and Ka bands today, with Ku being added in Release 19. The earliest NTN work focused on L-band and S-bands, which were well suited for direct-to-device links because they penetrate the atmosphere well and support lower-power handheld devices. As NTN evolved, 3GPP added support for Ka bands in Release 18, explicitly defining NTN operations in the 17 to 20 GHz for downlink and 27 to 30 GHz for uplink, enabling high-throughput links for fixed terminals, aircraft, maritime systems, and enterprise gateways. The latest addition in the Ku band is in Release 19. This defines NTN operation in the 10 to 12 GHz for downlink and 13 to 14 GHz for uplink. Depending on the satellite architecture, the signal may be processed on board or simply relayed to a ground gateway. In a transparent payload system, the satellite acts as a bent pipe, forwarding the RF signal to a gateway connected to the terrestrial 5G core. In a regenerative payload system, the satellite hosts a full or partial 5G base station, performing baseband processing in space and reducing the load on ground infrastructure. Either way, once the traffic reaches the 5G core, it is routed like any other 5G broadband session. The result is a high-capacity link capable of delivering hundreds of megabits per second or even gigabit class service to homes, ships, aircraft, and remote enterprise sites, all using standardized 5G technology rather than proprietary satellite protocols. Note that even though both broadband and D2D service use 5G NTN technology, there is a difference in application. Under the hood, the two services require completely different antennas, link budgets, waveforms, power levels, timing models, Doppler handling, and satellite payload designs. Direct-to-device 5G NTN works very differently because a smartphone cannot use a dish or high-gain antenna. Instead, the satellite creates many small, tightly focused spot beams designed to match the limited transmit power and small antenna aperture of handheld devices. When a phone loses terrestrial coverage, it can detect the satellite cell and begin the 5G NTN access procedure. The phone performs timing and frequency compensation to handle Doppler shifts and long delays, then attaches to the satellite network using the same authentication and mobility management procedures used on terrestrial 5G. The satellite either regenerates the 5G signal on board or relays it to a gateway connected to the 5G core, where the user's traffic is handled just like any other mobile session. Early implementations have low-rate data, but as satellites with larger antennas and more advanced onboard processing come along, direct-to-device links will evolve from basic emergency messaging to full two-way broadband connectivity, all without requiring any hardware changes to your phone. The use of intersatellite laser links together with the integration of 5G NTN makes the Bureau 1440 Constellation one of the most modern. Their late start allowed them to adopt all the best practices and standards which were not available when the pioneers like OneWeb and Starlink were developing their constellations. The OneWeb constellation doesn't have intersatellite laser links and is now struggling to deploy a new constellation of satellites with intersatellite laser links in order to catch up with the likes of Starlink. Starlink's primary broadband service is not currently 5G NTN ready. It uses a fully proprietary physical layer to control the satellite hardware, a proprietary medium access control layer to manage radio channels, proprietary user terminals to send and receive signals, and a proprietary routed architecture to move data. Starlink's new direct-to-cell service also operates using 4G LTE and not 5G NTN. The 3GPP work on 5G NTN began with a steady phase that concluded in 2019, but the actual normative specifications were not finalized until 2022. By the time those standards were available, Starlink had already designed and began deploying its proprietary system, so it could not have been based on 5G NTN from the start. SpaceX has stated its plans to support 5G for direct-to-cell in the future and may eventually adopt 5G NTN more broadly to improve interoperability with terrestrial mobile operators around the world. Amazon's Leo is also not currently 5G NTN ready. Like Starlink, its system is entirely proprietary, built on a custom-designed Prometheus baseband chip and proprietary terminals. Amazon has not announced NTN compliance, but they are watching the standard closely. In contrast, AST Mobile is explicitly targeting 5G NTN. Their entire business model centers on direct-to-device connectivity using 4G 5G waveforms, allowing unmodified phones to connect directly to their satellites. Their service is built on 3GPP Relay 17 standards, and their radio frequency profiles were recently standardized under 3GPP Release 19, making them one of the closest to full 5G NTN compliance. Like Starlink and Amazon Leo, Bureau 1440 is actively developing a direct-to-cell capability for its constellation. A key enabler is its prior integration of the 5G NTN protocol standard. The company has been implementing 5G NTN communications since May 2024 and has designed its network to function with orbital 5G base stations, which makes adding D2D service a logical next step in its technological roadmap. In late March 2026, the Russian State Commission for Radio Frequencies approved frequency allotment for both Bureau 1440 and private space company Sputnik. This authorization allows them to begin testing direct-to-smartphone connectivity, though commercial use is restricted until early 2029. The first stage of the constellation will cover about 300 satellites for broadband internet access, with the second stage adding an additional 900 satellites. The goal is to complete stage 1 and launch the satellite broadband access into commercial operation by 2027. Initial service will be limited to military, government, and business use until the constellation is expanded to about 1,000 satellites, when the network capacity is enough to handle customer traffic without massive slowdown. On March 2026, the first batch of 16 satellites were successfully launched into a parking orbit. They separated from the Soyuz 2 launch vehicle and were taken control of by Bureau 1440 at their Moscow control center. After the completion of the checks and launch of the onboard systems, they began to move the satellites to their target orbit. Commercial operation of the satellite broadband data transmission system will begin in 2027, after the first tests have taken place in 2026. In order for the system to be considered service-ready, a number of improvements need to be made. They will first need to establish stable operation of the constellation in Russia, provide coverage, debug services, and go through all the stages of pilot operation. Only after that will it be possible to talk about reaching the global stage. They continue to refine the system to ensure that the constellation provides subscribers up to 1 gigabit per second downloads with latencies of less than 70 milliseconds. In order to provide acceptable coverage, they will need at least 288 satellites. Starting with a smaller constellation is easier to maintain and cheaper to run, and the constellation size can always be expanded later to meet new demand. The company estimates 2 million potential subscribers in Russia and up to 12 million end users worldwide by 2035. Comparatively, in 2025, Starlink doubled its customer base, surging from 4.5 million to 9 million active users worldwide across 155 countries. Starlink expects to reach 14 million by 2030. The requirement for consistent high-quality coverage directly determines the required number of satellites in the constellation. Orbital mechanics dictate that to guarantee at least one satellite is always above a minimum acceptable elevation angle, typically 20 to 40 degrees for good service for every point of the coverage area, a certain number of orbital planes and satellites per plane are necessary. A satellite directly overhead has a short, clear path to the user. In contrast, a satellite near the horizon at a low elevation angle forces the signal to travel at much longer distances through a thicker layer of the Earth's atmosphere. This longer path causes greater signal attenuation and degradation, meaning that to maintain a minimum data rate or connectivity quality for the user, the satellite must use more robust but less spectrally efficient transmission modes. While adding more satellites can improve coverage and total potential capacity, it introduces a critical counterforce: radio interference. As more satellites populate similar orbital regions, their signals begin to interfere with one another, especially when reusing the same frequency bands. The total bandwidth granted to a service sets the absolute upper limit for potential data throughput. It is the size of the pipeline. Research indicates there is a fundamental limit to spectral efficiency, the data rate achievable per hertz or bandwidth per unit area. Beyond optimal satellite density, the network hits a point of diminishing returns. Adding more satellites actually reduces the overall system capacity because the increased interference noise outweighs the benefit of having more transmission points. Therefore, the final upload and download capacity for end users is not a simple sum of satellite numbers alone, but the complex product of finite spectrum, the efficiency dictated by viewing angles, and the carefully balanced density of the constellation to manage interference. The Russian government is supporting this project by subsidizing rocket launch costs amounting to about 25% of the total initial cost of the project. Russia faces a critical bottleneck in its ambitions to deploy the Sphere, Sputnik, GoNet, and Bureau 1440 constellations, a severe lack of cost-effective rocket launch capacity. This bottleneck stems directly from its failure to develop a proven, reusable rocket, a technology pioneered by SpaceX that has dramatically reduced the costs and increased the tempo of satellite deployments. Russia's current workhorse, the Soyuz 2 rocket, is an expendable system. The reliance on Soyuz 2 rockets complicates scaling, as it will take about 20 rocket launches to meet 300 satellites in orbit. That's 65 rockets, each carrying 16 satellites to reach 1,000 satellites. Relying on it to launch thousands of satellites would be slow and prohibitively expensive, creating an insurmountable logistical and financial barrier to building a competitive mega constellation. But a cheaper Soyuz 5 rocket is almost ready to help reduce the cost. The medium-lift rocket will halve the cost of launch, putting about 35 satellites per launch in orbit. This single-engine booster rocket is almost as cheap as the reusable SpaceX Falcon 9, even though it's not reusable, probably because it's a single engine and engineers are cheaper to employ in Russia. The first new Soyuz 5 rocket was launched in April 2026. A second test will occur in 2027, and if the third is successful, then it will go into full service by 2028. The Soyuz 5 is a two-stage rocket capable of launching up to 17 tons of payload into low parking orbit, twice as much as the Soyuz 2. It will be the second most competitive rocket in the world, only behind the reusable Falcon 9. With launch cost of $3,200 per kilogram of payload, it's 40% cheaper than the Soyuz 2 with about $5,500 per kilogram, and less than the Chinese Long March with $4,000 per kilogram of payload. The SpaceX Falcon 9 costs about $2,800 per kilogram to launch, but they charge about $5,000 to $7,000 per kilogram to outsiders. Russia's lack of reusable rockets is a fundamental strategic constraint that slows down its entire satellite constellation strategies, so the government is funding the development of reusable rockets. The Amur LNG is a partially reusable methane-fueled medium-lift rocket being developed by Roscosmos subsidiary Progress. A prototype rocket is being prepared for hopper tests in 2026. Originally, there were ambitions for first flight around 2026, but realistic estimates now point to a maiden flight no earlier than 2029. The rocket is intended to carry payloads of up to 9.5 tons to low Earth orbit in a reusable configuration. Russia cannot begin serious mass deployment of its Sfera or Bureau 1440 satellites until early 2030s at the earliest. In the meantime, they will probably use the Soyuz 5 and Soyuz 2 launch vehicles to start populating their constellations. Luckily for them, they have planned a limited constellation of about 1,000 satellites, not 10,000 or 40,000 like the Chinese and American companies are aiming for before 2030. But this comes with its own disadvantages. By the time they are ready to launch a globally available constellation, SpaceX's Starlink, Amazon's Kuiper, and the Chinese duo of Guowang and Qianfan will likely have established mature global networks with millions of users, making foreign market prospects for them extremely difficult. Among the first private clients of the projects are large Russian companies, Russian Railways, Aeroflot, mobile operators Vimpelcom, Megaphone, and mining companies like Severstal, Transneft, and Alrosa. In 2025, Bureau 1440 signed agreements with railway operator RZD and airline operator Aeroflot to install custom terminals to provide broadband internet for travelers. The agreement aims to integrate broadband into a wide network of rail routes, including the Moscow to St. Petersburg high-speed railway and the long-distance services like Trans-Siberian Route. The latter journey, spanning 6.5 days from Moscow to Vladivostok, currently has about 4 days without connectivity, a gap this service is designed to fill to make the trip more enjoyable to travelers. With about 33% fiber cable penetration nationwide, low coverage in Siberia, and near zero in Arctic zones, Russia's own territory offers Bureau 1440 a sizable captive market. Russia is attempting to turn the Western technological isolation into its advantage, creating a self-reliant system for itself and marketing it as an alternative solution for other nations wary of digital dependency on the West. They will be targeting nations that are either geopolitical partners like Iran and Belarus or members of the BRICS and non-aligned bloc wary of Western technological dominance. Of the large countries, the easiest countries to access will be countries who already have good relationships with Russia. Countries including India, Brazil, South Africa, Egypt, Iran, Turkey, Bangladesh, Vietnam, Indonesia, Ethiopia, and Nigeria, where Russia is developing or agreed to develop nuclear plants. Most of these countries wouldn't want to be totally beholden to only Western providers and would most likely hedge their bets by bringing on board Russian or Chinese providers. In markets wary of China's digital expansion like India and Vietnam, Bureau 1440 will position itself as a political neutral provider. It will have the opportunity to fight for market share in high-growth, low-connectivity nations with low terrestrial coverage and huge populations including Ethiopia, Nigeria, Bangladesh, Indonesia, Iran, Pakistan, Brazil, Mexico, and Vietnam. It won't have access to Western markets, but that's not a huge loss because Western markets like Western Europe, Japan, Korea do not have that many people without internet anyway. They are densely populated and already have fiber optic internet. The American market is also already saturated with competition. It has Starlink, Amazon Leo, and AST Mobile. Many regions of Africa, South America, and parts of Asia lack comprehensive terrestrial internet infrastructure. A satellite solution is the most practical way to provide nationwide coverage. The Russians will position this system as a cost-effective and sovereign option for governments looking to rapidly digitize their economies without ceding control to foreign corporations. They will use established diplomatic, military, and economic ties as a gateway, offering a bundled package of satellite connectivity along with other infrastructure projects like nuclear reactors or as part of a broader strategic partnership. For nations also facing or fearing Western sanctions, the Russian alternative can serve as sanction-proof and operational independence. But for export success, the system must ultimately prove to be reliable, affordable, and user-friendly. While targeting the global south, Russia will still compete with Western commercial offerings and Chinese Constellations, which pursue similar geopolitical strategy with potentially greater financial resources. But most global south countries, in order not to be totally dependent on one pole, would most likely choose to have companies from both the east and the west. The deployment of LEO constellation services in Russia will produce a significant positive economic effect, primarily through the integration of Russia's vast and remote territories into the national digital economy. By providing high-speed, low-latency internet where laying fiber is impractical, it will address the core digital divide and unlock significant socio-economic benefits in the remote corners of the country. Initial integration will focus on logistics and transport sectors, such as providing connectivity for commercial airlines, ships on the Northern Sea route, and trains on the Trans-Siberian routes. It will provide connectivity to remote industrial sites in sectors like oil and gas and mining, enabling real-time data transfer, automation, and improved coordination. For public services and e-government, satellite internet will eliminate the need for arduous, expensive travel to administrative centers. Residents will be able to complete all paperwork online, applying for passports, driver's license, permits, or social benefits through the government portal. It will also enable participation in remote court hearings and access to other digital state services, fostering inclusion and streamlining bureaucracy. Residents in Arctic regions face the most urgent need for affordable low-orbit satellite constellations. The deputy governor of the Nenets Autonomous Okrug announced his excitement for the new Bureau 1440 project. He explained that geostationary orbit technologies are expensive and inefficient and are not getting cheaper or any better. He emphasized the status quo where residents pay exorbitant sums of money for speeds as low as 256 kilobits per second is untenable, and announced the regional government plans to launch a pilot in 2026 and become the first region to test the project. In education, connectivity will revolutionize learning. Students in remote schools would be able to participate in live interactive video lessons and access vast digital libraries and online courses, effectively bringing the classroom to the tundra or the taiga. Teachers could engage in continuous professional development through remote training, elevating their overall quality of education. This will directly promote equal opportunity, dramatically narrowing the educational gap between children in major cities and those in settlements in the Arctic like Tiksi or Dixon. The impact on healthcare would be profound, maybe even life-saving. Reliable broadband will enable robust telemedicine, allowing local physicians to conduct video consultations with specialists in regional or national centers. This will facilitate remote diagnostics where X-rays and ultrasound images can be transmitted for immediate second opinions. Crucially, it will enhance emergency coordination, speeding up medical evacuations. On a social and cultural level, affordable high-quality internet will reduce the profound isolation of remote life. Families will maintain close bonds through seamless video calls, while access to streaming news, entertainment, and cultural content will improve the quality of life in remote villages. For indigenous communities, it will offer powerful tools for cultural preservation, such as creating digital archives and facilitating online language courses. Russia's vast and unforgiving geography presents a profound connectivity challenge, with countless remote settlements lying far beyond the reach of terrestrial broadband infrastructure. Towns like Novo-Urengoy in the Yamo-Nenet region and Dudinka in Krasnoyarsk Krai are geographically isolated from fiber optic backbones, forcing them to depend on expensive, slow, and often unreliable satellite links. This isolation is particularly acute for smaller, isolated communities like Udachny, Sunta, and Yuba. For these populations, each under 20,000, the immense cost of laying thousands of kilometers of fiber across permafrost and remote terrain renders the project economically unjustifiable. Satellite broadband will be of great service in these communities. Connectivity is a catalyst for development. This service will empower digital entrepreneurship, allowing local businesses to market and sell their goods like reindeer meat, fish, or handicrafts directly to national and international markets. It will open the door for remote work, creating possibilities for residents to take on IT, consultancy, and other knowledge economy jobs without leaving their communities. The tourism sector could flourish through better online promotion by offering reliable internet to visitors exploring the Arctic. The enhanced connectivity will significantly boost security and emergency responses. It will enable reliable early warning systems for natural disasters like floods and improve coordination between rescue services during accidents. It will also support the monitoring of Russia's vast borders and critical infrastructure through connected sensor networks. For a big nation, it's a foundational project of technological sovereignty. The conflict in Ukraine has starkly demonstrated the strategic necessity of a sovereign, secure, and resilient satellite communications system. The Russian military is a foundational customer, requiring unblockable command links, intelligent dissemination, and connectivity for deployed units, especially in remote regions like the Arctic, where Russia has significant strategic interests. However, these benefits come with substantial economic costs. The financial outlay for building, launching, and maintaining a mega constellation is enormous, with estimates for Russia's project reaching nearly 5 billion. But with the coming of AI, providing internet to every remote village should be worth the cost. Having your own satellite constellation saves the country from funding other nations' space companies and rather helping develop your own local space industry. From a strategic perspective, a sovereign LEO constellation is a top priority for the Russian state. It will provide a military, government, and security service with secure, independent, and highly resilient communication channels that is less vulnerable to interception, blocking, or foreign influence. This reduces critical dependence on foreign technology and infrastructure, ensuring the state remains connected during geopolitical crises or conflicts.